Hi, welcome to the Magnetic Force intro video. This is the third video of the New Electromagnetism V5 video series. New Electromagnetism is the fourth paper of EtherealMechanics. Now this is a redo. This is a redo from the one that has been released for Patreon members. The reason why I had to redo it is because it didn't flow well from the previous videos that have already been premiered. So I changed the introduction to make it flow better. I also added just one more piece of information that I haven't released to Patreon members, but I don't think they're going to complain too much about that. So what we're going to introduce is the magnetic force model, and then we're going to introduce the fragment model of conductors, and then going to derive the fragment-to-point interaction that we're going to then use in later videos to derive a lot of interesting effects. You know, what is the VIM or EMF induced from wire to wire? What is the magnetizing force between conductors and magnets, and etc., etc., etc. The only thing I'm going to do new here is show how the legacy flux model actually arises from the magnetic force model. And that what we have been using for the past 150 years is basically a special case of new electromagnetism. And this should be very interesting. It's really no new technology, so my Patreon members, you know, I don't think they're going to complain too much. They're going to see this at least 6 days before everybody else, but usually I give my Patreon members at least 4 weeks, but this isn't really new technology. This is just showing how the old comes from what we've already seen. So the magnetic force model is derived in the Electrogravity series of videos and the Electrogravity paper. And the paper is the third paper of EtherealMechanics, and this is the video series code. Okay, right now we're showing everything in legacy units. We're doing that to kind of make things not so traumatic to any people that are new that are looking at this. Essentially, everything that's in blue is in legacy units. This is force in kilograms meters per second squared. If we did not have the km here, the natural units of this would be amperes squared, or square amperes. Okay, and this is not a vector equation per se. This is actually a vortex matrix equation. This brackets are here to indicate that this division of two vectors forms a matrix. There's a lot more degrees of freedom here than you will ever find with classical electromagnetic theory. And this actually forms a vortex around charges in motion. Anyway, let's get on with the derivation. Oh, and this is the alternate representation. This is the representation you will find in these two different representations you'll find at different places. They mean the same thing. Okay, both of these are inverse square models. Now, the ultimate goal is for us to take two arbitrary conductors, and these could be magnets too. One we're calling the source conductor, the other one we're calling it the target conductor, and we're taking the current that flows in the source wire and computing its effect on the target wire. Now, this source wire could be in motion. This is the velocity of the source wire. Okay, there could also be rotations. There could be all kinds of stuff going on with here, not just translation, but there could be rotations as well. And we have the same parameters for the target wire. And the way we do all these calculations is we break these arbitrary loops up into fragments. And differential lengths of wire we call fragments. It's easier to say fragment than it is to say differential length of wire. So that's just a terminology. Okay. And the velocity of this source differential length of wire is the velocity of the entire wire structure. We're assuming no flexing going on, but you could count for that too if you like. Again, this is a simplification. You got the same thing going on with the target fragment. So what we're going to do, we're going to show everything as a little target fragment. This is the differential length of the source fragment. This is the current in the source fragment. And this is the velocity of the source wire. This is the entire structure. But since right now we're just talking about everything moving together, that's going to be the velocity of an individual fragment. Okay, this is the differential length of the target. Again, it has a current, and it may or may not have a current depending on the situation. Okay, and this is the velocity of the target wire fragment. Now, what we're doing with each one of these fragments, each wire fragment has a whole crap load of positive and negative charges. Now, we're trying to be charge agnostic here. So, because electrical engineers use positive charges as the moving charge, and the proper thing is that electrons are the moving charge. So we're not going to make a distinction. You just have to add in the signs you like at the time you do the calculation. We're keeping these completely charge agnostic. So we're representing dark blue as what would be the mobile conductors, okay, and dark purple, which would be the stationary, or the charges that remain with the wire. In the normal wire, these would be the protons and these would be the electrons. In each wire, we're considering it to be completely charge balanced. The number of positive and negative charges completely equal. Okay, therefore, if you were to push this wire into motion, because you have equal and opposite charges in motion, there would be no net field generated by this wire in motion. This is an important point. We're going to come back to this, and we're going to show you there's other cases where the velocity of the wire can be completely eliminated from a lot of computations. So when we talk about conduction current, we're talking about a couple of the mobile carriers. For physicists, these would be electrons that would break free from the structure and go into motion. So this QC is the conduction charge, the quantity of conduction charge. That's not the number of electrons, that's the total charge. That would be the number of electrons times the unit charge of an electron. That's the total charge that's conducting. And the velocity of this charge is Vc, which is relative to the wire. Relative to the wire. Now, what's happening here is because these charges are now, and I'm showing them kind of pushed a little bit away. This happens all throughout the body of the wire. This is just a representation that these guys are now in motion. And because these guys are in motion, the ones that they originally balanced now become uncovered or unbalanced. And this is important because when we do our calculations in the future, we're not going to consider the rest of these charges. That just becomes a chore. So all we're going to do is when we consider each differential length, we're going to consider mobile carriers, which have a velocity relative to the wire, and this would be the total charge of the conduction charges. And the unbalanced charges is QU for the unbalanced or uncovered charges. Now, in the old paper, New Electromagnetism, which is 25 years old now, we came up with this wire fragment system. But in there, instead of calling them uncovered charges, we call them stationary charges, which is kind of a misnomer because if the wire fragment's in motion, they're no longer stationary. Okay, but just so if you go back and look at that paper, that is a terminology that is used, and it's almost the same. There's a couple of improvements. There's a lot of improvements with the new wire fragmentary system. So let me put this fragment in motion, and then let's look at the complete charge velocity. That's charge times velocity. So let's first work with the conduction charges. Since the conduction charges are moving relative to the wire, their total velocity is going to be the velocity of conduction plus the velocity of the wire times the quantity of charge that's in motion in coulombs, not number of charges. And because the uncovered charges only move with the wire, then their velocity is just the velocity of the wire. And we can add that there. Now we have the total charge motion. So first thing we can replace is we can replace QU with the negative, its equivalent, which is the negative of QC. And then what we see is that the velocity of the wire cancels out, giving us the illusion, the complete illusion that the field moves with the wire. The velocity of the wire is the velocity relative to the medium. And because that completely cancels out, it gives the illusion that the field moves with the wire. That's part of the illusion of classical theory. Again, once you account for all the proper charge motion with respect to the medium, you get the illusion that the field moves with the wire. Certainly, we can say the effect looks like it moves with the wire. Let's continue. Now this goes back to EM01 transvariance. This result shows that a magnetic experiment is unaffected by the motion of the experiment through the universe. And this includes the acceleration of the experiment. And this is the wonderful gift that was talked about in EM01, the first paper of EtherealMechanics, called transvariance. The gift is nature's way of allowing us primitives to obtain repeatable observations in spite of our varying motion through the universe. Because imagine if at different times of day or night or different times of the season when our velocity through the universe is changing, that our experiments give different results. We probably would have been many more centuries before we'd been able to figure things out, because the results we would have gotten would change day by day, hour by hour. So this beautiful gift gives us the illusion that our experiments we do on a benchtop are the same as if we're standing still. That is a wonderful gift that's talked about in the first paper of EtherealMechanics, transvariance. Okay, getting back to the wire fragment model now. This is the full parameterization. Okay, we have the differential length of the source fragment, the current in the source fragment. This is the velocity of the source conduction. This is the quantity of source conduction charge. This is the quantity of source uncovered charge. This is the velocity of the source wire, and basically everything the same, just the subscript changed to T for the target fragment. Now, let's talk about some identities here. Okay, so one thing we know that we've shown in the paper, and we've shown many times, that the current in the source times the differential length of the source is equal to the quantity of the source charge times the velocity of the source charge. And again, that's relative to the wire. Okay, and the quantity of source charge is equal to the QSPM. This is the quantity of mobile carriers per meter. Quantity of mobile carriers per meter. In the paper, we describe how you compute that. And that's mobile carriers per meter times the differential length. And from here, we can compute the velocity of the source charges by taking this and substituting this into it and dividing blah, blah, blah. You can figure out how to do that. That's pretty easy. Okay, and then we get all the same exact things for the target side. And again, the identity that the uncovered charges is equal to the negative of the conduction charges, and vice versa for the target fragment. Okay, so that's the parameterization. I know I went over it quick. Oh, and the distance between them is the position of the center of the target minus the position of the center of the source, and that provides a vector from source to target, which is defined as r. So let's begin the derivation. So what we're going to do is we're going to take our magnetic force model, and we're going to compute both the effects of the conduction charges on a target charge. This is green because we're being agnostic. It could be either a conduction charge in another wire fragment, or it could be an unbalanced charge in another fragment, or it could just be a lone proton or a lone electron sitting out here. It could be any sign. So we're leaving it charge agnostic right now. We're just putting color green on it. So we're going to compute the conduction charges against that, and then the unbalanced charges against that to get a base model. Okay, so let's start over here. The conduction charge, QSC, times the velocity of the conduction charge plus the velocity of the wire, plus the quantity of the uncovered charges plus the velocity of the wire. That is our QSVS, which we can replace QSVS. We can move this scalar inside to do this, and that replaces that. And then we divide by r, which is the direction from the source to the target. Okay, then we replace that the Q of the uncovered charges in the source are equal to the negative of the VSC, and this whole kit and caboodle resolves down to this. Now we're going to put this part in later. This requires us to understand something. This is actually a derivative of r, and this has to be handled a little bit specially here. And that's our derivative of r. essentially. Okay, now when we come down here, we write it down for the next page here, and we understand from the identity we can replace QSC times VSC, which works out to the current in a source fragment times the differential length of the source. And at this point, the field intensity that we're seeing, this represents the field intensity, is totally decoupled from the velocity of the wire. And that's why the field intensity on the left side of the wire and the field intensity on the right side of the wire, as the wire is moving, is unaffected. And that's why Albert came up with the idea, the only way to explain why a wire gets the same field on both sides is because the field moves with the wire, which again violates a lot of the laws of physics, but it gets the right answers. Okay? Who cares if we violate the laws of physics as long as we get the right answers? That seems to be what physicists rely on. Okay, so by properly accounting for the velocities of all the charges relative to the medium, we get that illusion, that wonderful illusion that makes it look like our experiment is standing still. So let me make one important point before we continue. Classical theory, which has been around since the 1880s, although it fails a lot of the rules of acquisition, it gets good results for all of this stuff down here. These are experiments. The only place it really fails is in self-induction. Okay, now these W's here only mean that it gets the right answers, but it has more egregious violations of the rules of acquisition here. I should probably put these back to green. I only really need this here. But the critical point is that it took me a lot of time to come up with a field theory that does not violate the rules of acquisition, does not violate causality, does not violate locality, does not violate ambiguity. And unlike classical theory where the field has to rotate with the wire, in New Electromagnetism version 1 and version 3, I tried a field that moves with the charges. And that worked okay for things that are translating, but it fails when systems are rotating in certain cases. These are rotating systems right here. It failed okay. It's okay for the homopolar generator, but it failed miserably for the paradox 2 through 4. Okay, and so what the field model is very interesting. What you have is, as the pretons move through the field, they're disturbing it. And even though it looks like the field is moving with the preton, which is what I originally thought, it's actually moving relative to this medium. This medium out here, shown by the white, is stationary. So that is the way that solves both problems, and it does not violate the laws, the rules of acquisition. Okay, it has the appearance that it's moving with the charge, but in fact it's actually a stationary emission. Okay, its velocity relative to the emission at the point where this guy, see us chugging along, every time it creates a field line, that field line now is moving relative to the medium. It's expanding out radially from the medium. It has nothing to do anymore with the velocity of the charge. So there's where you get that illusion that the field is moving with the charge when in fact it's stationary with respect to the medium. And that is the answer that solved everything. That is the pretonic field. Now, if you want to see some examples of this, we have plenty of examples in plain sight. When you have a ship coming in for harbor in calm water, you can see that this V, as long as the ship keeps moving at the same speed, this V is going to look like it's moving with the ship. When in fact, once the ship creates the disturbance, that disturbance is moving relative to the medium, the water. Okay, and that is where you get the illusion that the field moves with the thing that created it. That, again, is an illusion. And the part that took me the hardest was when things are going around in circles. That was the hard part. That was the part that took the longest time. Okay, so I want to get now to the final part of the derivation that we're going to use to show you something wonderful. Okay, this last part of the derivation, we still need to substitute the velocity of the target and the velocity of the source. Now, this part here, when you go back to the original derivation in the electrogravity series, this is actually the derivative of R. This is how quickly this mechanism here, this differential fragment, or this disturbance, is closing with the target. That's what that is. This is a derivative of the vector r. And I've shown the diagram in this because in this case, the conduction charges have a velocity, and so you would think that their velocity makes them close faster with the target than the uncovered or stationary charges. Okay, but that is where a mistake would occur. What's happening is you have to remember this is part of a much bigger loop. There's a fragment off to the left and a fragment off to the right. Now, although these charges are moving toward the target, relative to this fragment here, this charge gets lost into the next fragment. So it's no longer counted as part of this fragment. Likewise, the charge from the fragment to the left pops into the left side here, and therefore the total amount of charge motion, the net gain of charge motion in this fragment is not actually materially gaining on the target fragment. And because of that, for this equation for the fragment, you just have to put the velocity of the target source wire for Vs, and you don't account for Vsc in here. Okay, and so let's do that now, and that becomes the fragment to point magnetic force model. Again, this is the force on a target charge due to a differential source being a differential length of a loop. This can be an open loop or a closed loop. Okay, it's not limited to either. As long as you can get charges to move in an open loop, which you can, they do it in dipoles all the time, then you can compute the effect as long as you have the right charge distribution. You can have a different current for each fragment. That's what you would get with an open loop current moving in a dipole. Okay, and so this is the part we're going to use in later videos to compute the complete effects between magnets and wires and EMF and VIM and all that stuff. So that's what we're going to do in later videos. Now let me use this right now to show you something really interesting. So what if we had a second order system of pretons? Okay, so these would now be pretons that, let's say, inside an electron, because two pretons are an electron, and each preton would have half a unit charge each. And these spin at the speed of light. The axis of rotation would be a vector that goes down into the page. I should have shown a little X here. And since we're going to consider this to be negative current flow, this would be electrons moving through the wire. Now, what would be the force acting on this electron that is outside of a wire? Well, classical theory would say, and let's assume this wire goes on forever and ever and ever, and we're going to compute the effects of each length on this electron. Well, what you would get here in this case is that the electron would magnetize. In other words, it would orient itself so that it would rotate such that the current, the preton that is moving parallel to the current in the wire will align. So there'll be a lot more force pulling on this guy, and that will force the other guy to push away. So it doesn't matter what orientation this system starts out as, it's going to end up with the parallel moving electron, preton, coming closer to the wire, and the one that's moving the opposite direction being forced away. So you can think about it, it's going to magnetize, and that will force it into this orientation regardless of what orientation it starts from. Okay, so essentially it's going to magnetize this. Now, if I take this system and I'm going to rotate it that way, so we're going to be looking at the end of this wire and we're going to be looking at the side of this guy, it's going to look like this. So here's the X, meaning the current is moving down into the page, into the source fragment. And here is our second order system of pretons, which is an electron that is now, because of like moving pretons attract, dislike moving pretons repel. Now here's the interesting point. The distance between these are so small that the differential in force across this electron will be so tiny, so tiny, it'll be almost impossible to measure. And because it's very small and very almost impossible to measure, that's why classical theory says that there's no force on the electron, when in fact you do have forces that cause it mainly to rotate, to magnetize. Okay, now if I were to move this system around this wire in a path that looks like this, at each location it's going to orientate itself such that the parallel moving leg is going to be pulled tighter toward the central current, and the one that's moving in the opposite direction is going to be pushed away. So this is going to be, basically, it's going to magnetize. I could even put a magnet out there. And here I'm showing the magnet that the negative charges move on the edge this way, and the positive and the negative pull out of the page on this side. And again, the parallel moving side of the magnet is going to orient itself to the wire. But there's a big difference here, because the distance between the parallel current and the anti-parallel current are farther away. The net force on this magnet is going to be greater, and it will be measurable. Okay, so that's a fallacy out there, that there's no force on an electron. There is a force, that's why it magnetizes, but because these paths are so close together, the force is negligible and probably would not be able to measure with any equipment that I know. Now, let's go to the next step. We can actually trace out this path at different levels. Okay, and what does that start looking like? Now let's rotate it back so that the conduction current is going back up in the air. And what does that look like to you? Do you see what this is? The lights should be turning on. Yes, that is, if you go to anybody that's teaching you classical theory, that's trying to tell you what is a magnetic field, that is the diagram they show as lines of flux. And they believe that these lines are real. They're not real. This is a synthesis. This is an illusion that everybody sees. But it gives good answers, as we've seen. And that's the key. That's why the rules of acquisition are important. We need to be able to distinguish between what's an illusion and what's real. Because if we believe this is it and there's nothing more, then we're stuck. We're going to be using this for 150 years, as we have. Okay? And the important thing that I've shown you with new electromagnetism is we've gone on a long journey to get here, and at the end we arrive where we started and we know the place for the first time. Most excellent quote for coming back to where we started to show you what you really have out there. What you have is an illusion, but it gives good answers. And that's why the rules of acquisition are very, very important. Okay, because even though we get all the correct answers here, the correct answers are from models that are illusionary. And because they're illusionary, they don't really explain what happens in nature, what's going on at more fundamental levels. And so if we had telltale that in spite of the fact we good answers could show us where these models are wrong, then we could cut thousands of years off of sitting on our hands thinking we have the right models that explain natural phenomena when they're completely illusionary. Okay, and that's another quote from a physicist, and I can't remember his name, who said, the greatest obstacle to science is the illusion that we think we know what we're doing. And that's why the tells and the rules of acquisition are completely important. And I'm going to start producing the rules of acquisition video series after I'm done with the new electromagnetism releases. Okay, so in the next videos, we're going to take our fragment to point force model, and we're going to use it to compute the total forces between wires and magnets and all kinds of other fun stuff, and show you real results with the simulation software that you can measure and take to the bank. Thank you very much. Please become a Patreon member if you like what you see. $5 a month, and you'll see a lot of technology videos that I don't release. And a lot of technology videos are, in 99% of the cases, except for small things like I showed you today, they're usually minimum 4 weeks out before I release them to the public. And software and other things require a higher tier, but for the minimum technology videos, it's $5 a month. Please help out. I don't have a lot of time to do this. My JOB is my #1 source of income for this project. If you could help out and we can move this thing faster, and if I can get better videos by getting people that are really good at making videos, I mean, that would make things a whole hell of a lot better. So if you can, I appreciate it. This is the site. It still needs to be updated. I'm probably not going to get to it this weekend. It'll probably be next weekend, where I'm going to update all the links for all the new releases for new electromagnetism V5. It's not up to speed yet, but we'll get there. This is the blog site. Big shout out to Sebastian for setting this up. When I'm getting done with the new electromagnetism, I'll make sure to make more time to talk and get to know people here. I appreciate everybody, everything they're doing for this project. This is the new Premiere website. We have the old one. This is the one. It's EtherealMechanics.com. You can get there that way. If not, if this is broken, sometimes this breaks because I guess somebody doesn't like me. Then you just go to YouTube and look up EtherealMechanics. There's another website using EtherealMechanics, but they're talking about self-healing and something weird like that. This is EtherealMechanics 5686 if you want to get there. So anyway, thank you. I hope you enjoyed this video. No more voodoo physics.